If you were here for Jack's talk, the previous section, it was interesting. I thought of how Oxford University should have paid attention to his principles. I was wandering around Oxford one day, and I saw a new college founded 1379. I thought, didn't they realize that at some point this college wouldn't seem quite so new anymore? But they had stuck new right into the name, and they were stuck with it for 700 years, I guess. What I'm talking about is my attempts to apply generic programming principles, basically to achieve a high level of abstraction in an agent-based modeling system. And I'm going to quickly go over some of the stuff I've discovered. This is very much a work in progress. I'm exploring the system and working on achieving higher and higher levels of abstraction in it. Part of my inspiration here is Stepanoff and Rose's book, From Mathematics to Generic Programming. In some cases, I've been directly applying the kind of thing they talk about, but it's been more as a background inspiration for me as to how it's functioned in my project. The basic idea of the book comes from the work that's been done in mathematics to achieve higher and higher levels of abstraction. So we have something called addition, right? And everyone is familiar with addition from grammar school, right? 2 plus 2 is 4. But what's been achieved over centuries in mathematics is an idea of addition as a pattern rather than that concrete thing of adding 2 integers. So the pattern is that the operation going on has to be associative, commutative, and have an identity element. And I have mentioned the unknot there. We'll get into that, what that is briefly. So we can add clock time, and knots besides integers and reals and other things as well. What we want to do if we're going to achieve generic programming is, can I switch this to full screen view here? Let's see. Sorry. Okay, thanks. Mm-hmm. All right. Okay. Sorry, I'm just not I never present with that kind of look on the screen. It was distracting. So if we're adding clock time, we're doing addition modulus 12. If it's 8 o'clock and we add 8, we want a return of 4. If we're adding knots and we add the unknot to something, we want the original knot. The unknot is just a loop that adds no crossings to a knot. Agent-based modeling, just to briefly go over what this is, we're trying to generate complex macro behavior from simple rules. We have little packages of code and data that exist in an environment, are called upon to act. So the package is generating its own behavior. It looks around itself in the environment to see what to do, and it interacts with other agents. I'll give you a couple of examples. This is a forest fire model. There's just a simple rule for how trees in the forest fire behave. What will happen here is lightning will strike someplace randomly. It struck here, I can see, and then it burns out the neighboring trees. This is where the fire is red, and then the trees start to regenerate after a certain time, once the forest fire is passed. What's interesting is that we get very complex patterns of interaction based on very simple rules. That's the kind of thing we look for in agent-based modeling. If we can experiment, if we change the density of the forest, we get radically different patterns of how things are burning out. This is a Nobel Prize winning model. Thomas Schelling won the Nobel Prize in economics, and this model was a major reason. We start out, we just throw here blue and red to be uncontroversial and not get into any real world dynamics, just focus on the model. So we imagine there's blue and red agents, and what they want is they want to not be too small a minority in a neighborhood. So they don't care to have a segregated neighborhood, they just don't want to be the only red agent, the only blue agent in the neighborhood. What Schelling showed is we start with that. This started with a random distribution, and they just follow a rule. You have a certain minimal number of agents who you want to be like you in the neighborhood. And if you just set that at 40%, basically, you wind up after 20, 30 turns with a pattern where you're almost fully segregated. And this was a very interesting finding that the finding, what Schelling's model showed, was that you didn't need people to want to live in an all black and all white neighborhood to wind up with neighborhoods like that. So very interesting finding on his part. The goal here has been these models have been out for a while, but the goal with this project has been to try to push as much of the work backwards into library modules that make the actual model very easy to achieve. And these are just some of the library modules that exist at this moment. One of the things that these models typically have, which both the ones I showed you have, is the concept of space. So the trees burn out according to what trees near them are on fire. The agents move or don't move based on looking at their neighborhood and seeing how small a minority they are in their neighborhood. So we need a concept of space. Typically, this is done as a grid. It makes it simple to handle rather than handling a Cartesian plane. And if, when you need finer grained space, you put more cells in the grid. There's a limit to that, of course, but typically these things are done as grids. Now, when I began looking into this, what I found was the code I was seeing would go and each model would grab some area around it, around an agent, and collect the cells in that area, look at those cells and say, oh, there's a tree on fire next to me, I'm on fire. Or, oh, I'm the only red agent in this neighborhood, I better move. But it was just coded, each model would code its own way of getting this look. And then when if you wanted to make a move, there was a new bit of code as to where you could and couldn't move to. And as I worked on this, I got the idea that, okay, what I want is a general way. If this is my grid, I want to be able to grab this square neighborhood, or maybe a diagonal neighborhood, or a neighborhood that's a cross of some sort, or any combination of those, and pile them on top of each other. And so the idea of a grid view was developed. And then the grid view, it was possible to make each grid view a grid itself, but that looked, that seemed suboptimal because each one was going to have the cells itself if it was a grid. So what has worked out nicely is that all the grid methods, like find an empty cell, Jack is left, you can't tell me if my name was bad find an empty cell, you can pass it a grid view. So it'll find the empty cell in the grid by default, but if you pass it a grid view, it finds it in the view instead. And then every grid method has the option of passing a view, and then whatever you could do in the grid, move to an empty cell, collect the agents in a grid, or we can collect them in the grid view instead. So all the grid methods take an optional grid view, and the method is reduced to that view instead. And the view can be any arbitrary combination of cells from the grid. So your ultimate flexibility. For instance, if you had your kind of thing you might deal with if your agents were chess pieces and you had a knight that was trying to determine its own move, well, the cells a knight can move to are a kind of odd collection of things, right? But this kind of grid view could easily incorporate that, whereas something like just squares can't. We've been able to achieve a good deal of abstraction in our action loop as well. Every model has an action loop. If the agents don't act, there's no point to the model. It was found that pre-actions and post-actions were sometimes a good idea, and so we have loops that can be turned on and off with flags, and they're built right into the core engine so that each model doesn't have to code that loop itself. It just sets post-act true, pre-act true. The kind of thing you might want to do, for instance, in the forest fire model, if a tree sets its neighbor on fire, depending on the order they're called, that could set every tree on fire in a single turn. But that's not the idea. The idea is a tree that's on fire sets a new tree on fire, and the next turn, that tree sets one on fire. But if it's on fire when its act function gets called, it'll set other stuff on fire. So you have a post-action loop, and you set a next state and then set the state in there. Abstracting a pattern of an entire model is another kind of abstraction we've been trying to achieve. So in a paper I'm working on, my co-author and I have been detecting two population models in a lot of cyclical social patterns. So we have a fashion model that actually comes from Adam Smith, where you have trendsetters and followers, and this produces waves of fashion. The trendsetters adopt something, the followers follow. Well, there's a finance model with people who are value investors and people who follow charts. It's very similar. I programmed this model, and then I went to work on this one and looked for the commonalities and managed to push a lot of the code in the two models up into another model called a stance model, because the two populations are taking stances towards each other. What's our end time here? 10 minutes, okay. So in the action loop, I've been able to isolate a common pattern, and what this does, ultimately, we'd like social scientists to be able to program a simple Python statement about what the agent's doing, and we plug it into these things. So how does the agent respond to conditions? So we have this little pattern acting. We look around the environment, we evaluate what we saw. For instance, look at how many red versus blue agents there are around us. We do a calculation and then respond. In the case of the segregation model, you jump to an empty square if you don't like the neighborhood you're in. But this pattern is we found it again and again in many models, and so we're trying to see if we can fit as many models as possible into the pattern, because then we can just have plugins. So, for instance, here, a number of models might have an agent just jump to an empty cell if the conditions are such that the agent is unsatisfied. So that thing can be applied across any model that needs it. It's done once and applied again and again. Python itself is well suited to generic programming because it's typeless. We can naturally, Stepanov and Rose are working in C++. Stepanov, of course, did the C++ template library. And there you've got to do a lot of work because it's a strongly typed language. Python lends itself to this style of programming because there's no type on the parameters coming in and no type on the return. So if what we're returning is from our summation function is a new not instead of an integer, we just return the new not. Okay. Let's discuss briefly what I feel is something that's really come home to me trying to get these abstractions here. And reading Stepanov and Rose. In mathematics, the process which has played out over 4,000 years, something like that, was what were people starting with? They were starting with measures. And I said, I told my wife, I said, look, figured out how to get Stonehenge into my presentation. That's cool, huh? So people were trying to lay out a bunch of stones in a field and have them at the right spots, right? And so the sun rose over this stone at this time. Or they were trying to plow their field and not go into their neighbor's field or look to where to lay the irrigation ditches. So they were looking at common measures. And even up to the great Greek mathematicians, they're really still viewing these things as measures rather than an integer per se. If you look at Euclid, he's often talking about this measure compared to this measure, the square of this measure and the square of this measure will equal the square of this measure. So from that, you get the idea of natural numbers. We had zero, we get integers. Rational numbers were slower coming, polynomials, real numbers, complex numbers, groups, rings, fields. But this process of abstraction from this concrete activity of measuring took place over centuries. What didn't happen was someone sat down and said, hey, I got this neat idea of an abstract algebra of rings and fields, and said, hey farmers, here's an abstract algebra. I bet you might be able to measure with it somehow, right? That wouldn't have really been workable. The farmers probably wouldn't have appreciated this diagram when all they wanted to do was plow their field. So it's very much come home to me doing this project. As I pointed out with the stance model and the fashion model and the financial market model, what I did was I programmed the fashion model, I programmed the financial market model, and got both models working. Then started looking at, okay, what is common between them? I didn't start with the idea, I want a nice abstraction that I can generate all these other models from. The abstraction came from the concrete application. Now that's work in that you need to do refactoring as you build the abstraction. And I don't find that terribly taxing, though. Over years, I've gotten good heuristics for refactoring that seem to make it fairly trouble-free. And what you get, though, by doing it this way is you get abstractions that fit the concrete applications rather than trying to shoehorn the concrete applications into the abstraction. Python, I've been working in Python doing this project because it seemed perfect for it. So I've been learning it the last couple years. But I probably did 15 languages before Python, and so I very much like it, but I'm somewhat wrestling with some of the Pythonic ideas for how you should do things. The flat is better than nested is something that for this project I have not really been trying to follow. It definitely creates complications, and the reason for the dictum flat is better than nested is clear. It's clear to me when I'm looking at a piece of my code and I'm going, oh my God, which module is doing that? And, you know, it's my own code and I can't remember. This creates a complication. Now, the trade-off is that the end goal of this project is to have a social scientist who's not dealing with this machinery under the hood at all, and instead is just filling in templates with small Python functions, maybe not even Python at some point. We're filling in a form on the screen or something like that. Thinking of this trade-off, the evolution of the automobile seemed to me to be apt metaphor. So the Model T was much flatter. In those days, the car user either was a mechanic or pretty much brought a mechanic along with him. So you had a chauffeur who also knew how to fix your car because it would break down, quite regularly, and you had to just pop out and make it work again. You had those cranks and so forth. Now we've got really complex systems embedded in the car, and the average user has no idea what they're doing, but the average user can simply turn a wheel, press an accelerator, press a brake, and the thing works like they want it to. So it may be worth it. The end product is what tells it finally, but to bury a bunch of complexity to give very simple controls at the top level. So in terms of flat is better than nested, that's my evaluation of the trade-off I'm making here. Last thing, this is a project up on GitHub. Anyone who's interested in looking at it or contributing, I've had some of my students work on it with me, but I'd be anxious for more contributors, and we'll throw it open to any questions at this point. Questions or applause? Applause is always welcome too.
I guess, what is the difference between this and the sort of classic, like the idea of polymorphism in abstraction?
Yeah, so what Stepanov and Rose, let's see. I'm sorry, I'd have to look in their book again. But I guess the short answer is they're trying to achieve another level of abstraction higher than polymorphism. Yeah. Yes.
Where is this on the
I don't have the address in the top of my head. Sorry. Gene, if you search for Indra, okay. So the project name is Indra. Search for Indra, and you'll find it. Sorry. Yes.